merci. So first, thanks for the invitation. As Benoit said before, I'm not a mathematician, so if it's not fancy enough, please forgive me. What I want to tell you about is work that I've been doing with a postdoc called Doron Grossman. And what we are trying to do is start from microscopic, or I should say mesoscopic description of tissues, the vertex model that we just heard about, coarse grain that, and try to get macroscopic equations. In a sense, I want to start with this mesoscopic description and obtain some hydrodynamic theory of tissues. First, I want to, so I come from the other side of the street. I come from Institut Curie, which is just next door. And this is a cancer institute. So we are supposed to work on cancer. And the way we seriously work on cancer is we study multicellular spheroids. So these are a set of images of spheroids. The only thing I want to point out is that they're all more or less spherical, which tells you that they have some kind of surface tension. They tend to minimize their surface. There are other types of tissues that we are working on. One is the inner surface of the intestine. So that's an epithelial layer, a layer that lines the surface of the intestine. And it is unstable, and it makes these protrusions, these fingers that go inside. I won't talk about that here. My next example comes from development. These are pictures from the wing disc of Drosophila. And this is also a two-dimensional tissue, which is the type of tissues that people use to, that people study when they use vertex models. So this is the kind of stuff that I will talk about today. So something went wrong. So I want to do a few things. The first thing, I will say a few words about hydrodynamic descriptions of tissues. How can we consider a tissue as a material and do hydrodynamic with them? I'll go back very fast on the vertex model, and I'll show you that we use a modified version of the vertex model. And then I'll talk about the coarse graining, and I'll give you an example on growing tissues. So these are two spheroids now. The two spheroids are pushed against one another. And when they are pushed against one another, they fuse. And they fuse exactly like two droplets of oil would fuse in water. This picture looks very much like pictures that were done by people like Plato in the 19th century. If you wait long enough, you will end up with a spherical object, which is the sum of these two objects. And it's more than that, which means if you try to do it quantitatively, you measure the neck, and you look how the size of the neck increases with time. So you know how it should go for two drops. This is the classical law. The square of the size of the net goes like the original radius. It grows linearly with time, and the capillary velocity, which is surface tension divided by viscosity. So I told you already that there was a surface tension. If you can measure the surface tension, that will give you the velocity, and you see that the law works pretty well. It grows as a linearly with time. The only thing is that tissues are extremely viscous. The viscosity is like 10 to the 8 times the viscosity of water. So they flow, but they flow with a very slowly. Now, of course, there is another difference, is that in a tissue, cells divide and cells die. So if you want to write the conservation equation, there is a density variation, there is a flux, and then there is a division rate, and then there is a death rate. So it's a hydrodynamic, but with a number of particles which is not conserved. Even if you take the incompressible limit, and we heard about that yesterday in details, it tells you that the divergence of the velocity is not zero, it's a finite number, which leads to all kinds of weird effects, or at least effects that you don't expect intuitively. Now, there are two other things I should mention. First of all, a tissue is viscoelastic because at short times the cells are elastic, and there is an elastic modulus, an elastic shear modulus, which is of the order of the shear modulus of the cells. And also it's active. For me, a material which is active is a material that consumes energy at the scale of its constituents, so each cell consumes energy, and that's what makes the tissue active. So we can use all the things we learned in the recent years about active materials and apply them to tissue. Now, the division rate decreases with pressure, the death rate increases, and you can reach a pressure which we call the homeostatic pressure, the steady state pressure, where the growth rate, which is a proliferation rate, is exactly equal to 0. In this case, the tissue is at steady state, which means the number of cells is constant or fluctuates around the constant. So there are a few experiments that measure this homeostatic pressure. In some cases, it's positive, and in some cases, it's negative, which means that the tissue is not under pressure, it's what the biologists call under tension, which is a negative pressure. We found that in numerical simulations, but I have no qualitative explanation to give you on why the homeostatic pressure can become negative, and this is essentially what we were trying to figure out from our model. So that's the limit of macroscopic description. Then, if you look at epithelial tissue, you want to do a microscopic description. So there are 3 stages of development of this wing of Drosophila. I want to insist on the fact that and this is just like the last talk ended, that the cells are 3-dimensional, which means they have a height perpendicular to the tissue. And what you do in the vertex model is that you only consider the apical surface. So you ignore what's below. You can make a vertex model in 3 dimensions and take the limit where you go to 2 dimensions. In the best cases, you derive the equation of the vertex model in 2 dimensions. Now, the way you do it is you take so what's labeled here is the interface between cells, the membranes. You take the vertices, which this image gives this one, and then you join them by straight line. So you replace each cell by a polygon. And then what you want to see is how does this, I don't know, you want to call that graph, network, I don't know what the proper word is, evolve as a function of time. So you need rules for that. And the rule is that the forces are equilibrated at each point. A simple way to implement that is to write an energy. So the energy that everybody uses is that each cell has a preferred area. And I will consider that all the cells are identical here. So there is a modulus that brings the cell back to its preferred area. And each cell has a preferred perimeter. And there is a modulus that brings back the cell to its preferred perimeter. The simple thing that you can study is a ground state of the vertex model, which means a state of lowest energy. So that's, I won't explain what the coordinates are, but it will allow me to discuss the ground states. There are 2 types of ground states that you find, depending on the value of this dimensionless parameter, which is the perimeter divided by the square root of the area, that I call the shape ratio. If the perimeter is very big, you can always take the area R0, and you stretch the perimeter in such a way that you reach a perimeter which is equal to P0. So if the perimeter is big, you can make state where this energy is 0. And there are many, many states that you can make. So the ground state is extremely degenerate. You can transform one state into the other. So this ground state has a lot of soft modes, and the shear modulus vanishes in this ground state. If you go to small perimeters, then to minimize the energy, you have to make a cell which is the most isotropic as possible, and you can show that in this case you make hexagons. You can make them to the area which is A0, however, you cannot make the perimeter. In this case, which is a case I will call a hard solid, there is a finite shear modulus, and the ground state is a perfect lattice of hexagons. Now, the transition between these 2 states occurs for a critical value of this shape ratio, which is just the ratio of the perimeter to the square root of the area of a regular hexagon. So that's for the ground state. Before I go further, what I want to do is tell you a bit about the geometry of this vertex model and how we describe it. So I will start by defining a reference state. And what I define as a reference state is a configuration of the tissue at time t equals 0. So that's my original reference state. Of course, at a time t, the tissue is a little bit deformed. It's deformed because maybe at time 0 it was not at the minimum because there are forces and things like this. So the vertices have other coordinates that I call big X here. And what I will do is what people do in standard solid elasticity. I take the length of an edge in real space in the current state. There is a metric which is related to the derivative of big X with respect to small x. And I write that the length squared is delta x, which is the length of the edge, delta x mu times the metric. So what G measures is the elasticity of the tissue, is more or less a strain in the tissue. Of course, when the conformation changes, G changes, and time variation of G describes the variation of the elasticity, so it's the local flow of the tissue that relaxes to equilibrium. However, these are not the only transformations in the tissue, and as was said in the previous talk, there are topological transformations. So I drew one here. If you look on the top, the cell at the bottom left and the cell at the upper right are in contact, and then you can switch the link in such a way that there is an exchange of neighbor. This is known in the physics of foam, and that's called a T1 transition. That's a topological process. It occurs in my reference state. So as time goes on, if these topological transformations occur, they change the reference state as a function of time. And to measure that, I will characterize the tissue by what I call the network tensor. On each cell, I take the series of vectors that go around the edges, and I define the sum of delta xe, delta x mu. That's kind of the, I don't know if you want to call it the inertial tensor or something like this. It tells you about the shape of the cell. What this topological transition does is it changes Q. So there is a jump when the transition occurs of Q, which is a finite jump, but it doesn't change the metric. So these topological transformations, in a sense, lead to plastic deformation, and the change in G leads to elastic deformation. So there are three types of topological transitions. The first one is this T1 transition, the exchange of neighbors. The second one, which is drawn here, so in foam, they call that T2, it's cell death. That increases the average area locally because one cell disappears, so the other ones become a bit bigger. And there is cell division. So these occurs in my reference state. They change the reference state, and then the tissue is deformed by elasticity. They change Q, they don't change G, and you can convince yourself, as they are very local, you can still define a coordinate system. There is just a point where the transition occurs, where the metric is affected, and that's negligible. Now we know, because we studied that using our hydrodynamic model, that if you have a finite rate, for instance, of cell division, or a finite rate at T1 processes, that relaxes the elastic stress, and the solid where you relax the stress is a liquid. So because of this topological transition, if you wait long enough, the tissue is viscoelastic and it has a liquid behavior, which is the one I was talking about before. So in the following, I will cheat a little bit. I will modify the vertex model. I was going to say in a mathematical way, in the way mathematicians would do it. I will replace it by a model that I can use analytically. So instead of using the perimeter, I will use what I call the generalized perimeter, which is not the sum of the lengths of the edges, but which is the sum of the length of the square of the edges, which I can write as a function of the metric. And this here is just the tensor that I call Q mu nu. So in the following, I won't use the perimeter anymore. I will use that. If you are close to the reference perimeter, it's not too different. You can linearize, and at the linear level, it's more or less the same thing. At the nonlinear level, it's not the same. On all the properties that we could check, we found the same qualitative behavior. I will show you an example in a minute. And then the other thing I will do is I will try to express the area as a function of the two tensors I know, which is the metric and the network tensor. So the area is the square root of the determinant of the metric times the square root of the determinant of the network tensor times a number which is always of order 1. So this number is not constant. It depends on the number of sides of the polygons, except for triangles, which when it is always the same, it depends on how you deform the polygons. However, it doesn't vary very much. So I put the numbers here. Triangles are this number, hexagons are this number. You have cells which are which has 7 or 8 sides, which have still a higher value. What I will do in the following is I will replace it by some kind of average value. So what we did, I didn't do it, Doron did it. It generated a random tessellation of space, measured this factor S, and looked at the average value and the variance. The average value is here, it's 1.8, and the variance was between 5 and 10%, even if you stretch the polygons. Now, if you stretch them, you can make S very different, but you have to stretch them 1,000 times, and in a tissue, you never see that, so we decided that this was kind of irrelevant. And then this factor S, I can absorb in the parameters of my model. That's easy to do, and this is exact. So in the end, I will end up with a new energy, which has the area term, and I replace the perimeter term by this 2p minus 2p0, which is my generalized perimeter with respect to the reference ones. I insist on the fact that we did that because it allows us to do analytical calculations that we couldn't do otherwise. So now what I want to do is coarse-grain this model. So what I wrote on top is kind of a dream, is how I should do it. I should specify the configuration of a tissue edge by edge. Then I should look at all the configurations which lead to the same two values of Q and G, average over these ones, and then the tissue I could describe only as a function of G, the metric, and the network tensor. The idea which is behind is that I want to slow variables in space. And what I'm kind of saying here is that if I average locally, if I do the coarse graining, I will get functions G and Q, which varies over length scales which are much larger than the cell size. So that's kind of the hope. Now, one thing that I can do without going beyond that is I add another approximation, which is what people do when they study phase transition. I use a mean field approximation, which means I average locally, and I replace the function by its average. Of course, there are fluctuations around that. I could have written the terms due to the fluctuations. They are very long, so I didn't write them down, but you can expand in powers of the fluctuations if you want. Then I make the two variables continuous, so I have Q and G. These are the determinants, so this is the area minus A0 squared. This is the perimeter minus the perimeter squared. And the density is 1 over the average area of the cell, which is here. So now I have an energy functional, which is a function only of these two tensors, G and Q, modulo the approximation that I showed you. So I have two fields, and I can calculate the conjugate fields. The conjugate to G nu nu is a stress. So if you take the derivative of the energy density, which is everything before the dx, you get the stress. And there is a field which is conjugate to this network tensor that I call the network field. If I look at the minimum of the energies, these two fields should be zeros because they are exactly equal to the derivatives of the function. Now, I cheated a bit because it only depends on G and Q and not the gradients. In the term that I call that would be fluctuations, I could generate gradients if I wanted. I want to do simple things, so I haven't done that, but you could generalize the theory to include gradient of these two fields. Now the real, I will give you a simple example. So suppose I fix the topology. I do an experiment which is fast enough that there is no topological changes. So Q is fixed, and I want to see how the metric adjusts. So I assume my tissue is not at equilibrium, and it will relax to some mechanical equilibrium. What I have to write is that the stress vanishes, the derivative with respect to G mu nu vanishes, and I find two cases, which, as in the original vertex model, I will call the soft and the hard solid. The soft solid is when the perimeter is large. When the perimeter is large, I will find a solution where the area is A0 and where the perimeter is P0. And I wrote the expressions here. It only depends on P0 over A0. In this case, the area and the perimeter is compatible, or if you want to say it in another word, the system is not frustrated. I have two terms in the energy and they are both zero, so I can minimize area and perimeter independently. The energy per cell vanishes and there is no internal stress. Now you can calculate the critical value of P. It's when this stuff here vanishes. It's again what you would obtain for a regular hexagon. If you calculate 2p and a0 for a regular hexagon and multiply by the S factor that I eliminated, you would find this value too. If p is smaller than 2, as in the original model, there is no way I can minimize the two terms together. And what happens is that the tissue wants to be as isotropic as possible, so the two eigenvalues are equal, and you find a value of both G1 and G2, which depend on the stiffness and on this shape ratio P. In this case, area and perimeter are not compatible. The energy per cell doesn't vanish, and what it means is that each cell is under external stress. Of course, the total force on the cell vanishes, but there are internal stresses inside the cell. And in all of the following, I will come back to that. The properties of the tissue are different when there are internal stresses in the cell and when there are no internal stresses in the cell. Now, if I were to do seriously the coarse graining procedure, what I would do is I would first write a probability distribution with all the variables and then do the procedures that I was mentioning earlier, which means sum over the microscopic variable at fixed value of Q and G. However, I don't exactly know how to do that, and the reason why I don't exactly know how to do that is that I would need to write the dynamics of the cell at the scale of the cell, which means how do these polygons by which I describe the cell change with time, and that is a complicated story. So I won't do that. I will assume that I can define a probability to have Q and only work with that, and this naive guess is to say this satisfies the Fokker-Planck equation. So I wrote it here. This is a cell diffusion. This is a convection term with a flux in Q space. So this dt dq, which is the velocity in Q space, depends on Q and G. And then there is a diffusion in Q space. Of course, as I don't know the dynamics, I don't know what this is. And what I want to do is use the standard procedure that people use close to equilibrium, which is an on-Zager approach. The way I do that is I calculate, so I multiply this equation. I calculate the energy, I derive with respect to time, and then I calculate the average dE dt. It has three terms. One, which is this flux times what I call the network field before. There is a mechanical term, which is sigma dg. And then there is a term associated to diffusion. And what I will do is I will forget, in this talk at least, noise all over the place. So this term I will ignore completely. Moreover, I will assume that the mechanical relaxation is very fast, which means if I deform the tissue, it relaxes very fast to the equilibrium state. Very fast means what? Means very fast compared to the time scale associated with these topological processes. Cell division is 1 day. And if you look at the spheroid, the local relaxation is much faster than that. It's minutes or something like this. So that's not a bad approximation. So I ignore this term, I ignore this term. And this is eta mu nu times dtq mu nu, which is exactly the structure of on-Zager's approach. There is a flux. The flux is dtq. And there is what he calls a generalized force. So what I want to do is say that the flux is proportional to the generalized force, and there is a transport coefficient between the two, and I only use symmetries to find this. So what I'm saying is that dtq is minus eta times some awful tensor here. And then I added a second term. I added activity. What I mean by that is that cell division doesn't occur if you don't provide energy to the cells. So I want to add an active term by hand here. The only thing I know is that this active term should be a tensor. And the simplest tensor that I have is Q mu nu. Now, you could say there is G mu nu, but G mu nu if you're in isotropic state is the identity, and cells, when they divide, have a direction. So the one that counts here is Q mu nu. So this G is the rate of cell division when there is no stresses on the cell. When everything is equilibrated, the growth rate will be Q mu nu. Then I need to determine this transport coefficient, G mu nu alpha beta. So it has 4 indices, so I need 2 tensors. I have 2 tensors at hand. I have G and Q. So we wrote the whole term. It would take 2 view graphs to write all the possible terms. The one that we felt was the most physical was this one. So it has 2 products of Q. You could make the same term with 2 products of G, and one with G, one with Q. This one looked to us by far the most physical. For instance, there are constraints that when a cell divides, you want the area to decrease. When a cell divides, you want the perimeter to decrease. And when it dies, it's the reverse. This one ensures that. It has 2 coefficients, H1, and H1 defines the rate which is associated to the topological processes. This is just the unit energy. And there is a factor H here. H depends on the topological processes that occur. There's one value which is special. If you take H equals -1/2, you have to check it from the equation above. The area doesn't change. Now, of the 3 processes that I showed you, only T1 transition don't change the area. Division reduces it, and death increases it. So if I take H equals -1/2, it means I only have T1 transitions. Any value of H which is larger than -1/2 means that there is a certain amount of cell division and a certain amount of cell death. So growing tissues. There are 2 things that I want to discuss for growing tissues. The first one is what happens if you have a free tissue, which means a tissue without any force on the surface. So in this case, the tissue is at mechanical equilibrium. There is no force on the surface. So the mechanical equation is just sigma mu nu is equal to 0. And I already solved that for you. I told you what happens for a given Q when I calculate sigma mu nu. So it's different for a soft tissue and a hard tissue. For a soft tissue, you are at the reference area and you are at the reference perimeter. So A is equal to A0, P is equal to P0. For a hard tissue, the tissue is frustrated, so I don't reach neither the equilibrium area nor the equilibrium perimeter. And if you solve the equation, what you find in the end is that A is A0 times this factor, and P is just twice A0. Then I need to define the growth rate. Now, the way to define the growth rate is to take an area where the 2 tensors don't vary, and to calculate the number of cells. So this looks messy, but this is the density times the area. So this is the total number of cells times the area. And if you divide by the area, you have the total number of cells. So the total number of cells is just 1 over Q. 1 over square root of Q. And if I take the derivative, the growth rate is dt Q mu nu, and this is the inverse of the tensor Q mu nu. So if I know the tensor Q mu nu, what I get in the end is directly the growth rate. So if you do that for a soft solid, as everything is equal to 0, you find that the only thing that contributes is gamma 0. If you do that for a hard solid, you find gamma 0 minus something. So because I couple the 2 tensors Q and G, the cell division rate depends on the mechanical state of the tissue, and it locally depends on the stresses in the tissue. So this is a reference area, and this E is the energy per cell in the state where I find the tissue. So the energy per cell calculated when A is equal to Ag and P is equal to 2Ag. So that characterizes the internal stresses inside the tissue. If you know the internal stresses inside the tissue, what you will find is gamma 0 minus something. So these stresses decrease the division rate. Now, if you plug that back into the number of cells, you will find what you expect, that the number of cells increases exponentially with a rate which is a division rate. So that's not exactly what I'm interested in. What I'm interested in is the homeostatic state. So the homeostatic state, I have to put the tissue in a box. I let it grow. I wait long enough. And because the cells cannot expand, that increases the stresses, that diminishes the division rate, and I reach a steady state. So that's what I want to calculate. So if you fix a box, that fixes the metric if you assume that the tissue is homogeneous. So I can impose the metric, and I calculate the tensor Q. So this time, I look at the field conjugate to Q, and I say it's equal to 0. That will give me Q. If I know G and Q, I can calculate the stress. And what I want is the pressure in this steady state. The pressure, twice the pressure, is a trace of the stress in 2 dimensions, minus. So P, the homeostatic pressure, is just minus 1/2 G mu nu sigma mu nu. So we have expressions for that, but they're a bit lengthy. So what I did is I plotted the homeostatic pressure as a function of gamma 0. Gamma 0 is a growth rate when there is no stress on the cells. The growth rate that they would have if there are individual cells. There are 2 values here. P naught is 2 P naught. There's a 2 that missed here. Equals 3. That's larger than 2. So this is a soft solid. If it's a soft solid, when there is no cell division, the pressure is 0, or it's the external pressure. And if you increase the cell division rate, the cell divides, so they push on the wall, and the pressure increases. If there are internal stresses, which means if I consider a hard solid, for gamma 0 equals 0, because of these internal stresses, the homeostatic pressure is negative. So the region where you will find negative homeostatic pressure is when the cell division rate is very low. For instance, if you decrease the amount of energy that you give to the cells, gamma 0 will decrease, and you will reach this region here. Then there is another property which I guess is very model dependent, which is that if P0 is larger than the critical value, this curve here doesn't depend on P0. It depends on the other parameters of the problem. It doesn't depend explicitly on what I call the shape ratio. If you look at a hard solid, it explicitly depends on the shape ratio. Until a critical value of the growth rate, and above this critical value, you find back this red curve here, which is independent of the shape ratio. So there is a well-defined homeostatic pressure. It can be negative, but only if there are internal stresses inside the cell. And if you go to very fast division rate, all this doesn't count, and it's independent of the shape ratio. So that's kind of where we are. I just want to summarize the results. The important thing is that there is a difference between what I call soft and hard tissues. For soft tissues, there are no internal stresses, and I was going to say everything is simple. For hard tissues, the internal stresses play a role. For instance, they can dominate the homeostatic pressure in the results that I give you. There is a marginal tissue in the middle, which corresponds to a critical value of the shape ratio. Now, I told you that it was equal to 2. We added fluctuations to that. Fluctuations increase this number. So it's not 2. It's 2 plus something due to the fact that there are fluctuations in all the quantities that I showed you. Another thing that comes out very naturally from this approach is that the growth rate depends on internal stress. It also depends on the fact that there is not a mechanical stress in the tissue, which is extremely important in biology because it means that mechanics can regulate the properties of cells and tissues. And as I showed you, the homeostatic pressure can be negative. We made a number, or we are thinking of making a number of extensions to this work. The things that we already made is we looked at periodic extension of a tissue. So there are experiments at Institut Curie by Stéphanie Manchelot, where she takes cells of the intestine and she pulls at a finite frequency, which is a high frequency. High meaning minutes compared to the time scale of reaction, which are hours. And what she measures is the orientation of the cells. I saw that tomorrow there is a whole talk on that. What we find from that is that if you do statically, they align with the strain that you impose. If you do it at very large frequencies, they go perpendicular. So that's what we find. And we had done before a purely mechanical model using the hydrodynamic approach, which has these two limits and which has another intermediate limit between the two. You can also, and that's related to the previous talk, look at the viscoelasticity of the tissue. So this time, if you go slow, you can see the fact that at short times the tissue is viscoelastic and not elastic. One comment that I can make is that you could also think that the tissue is a yield stress fluid, which means that it's like if you do geophysics. If the stress is low, it behaves as a solid, and if you put a very high stress, it starts to flow. I don't know of any analytical theories for that, but we made a long time ago with a postdoc called Jens Elgeti numerical simulations, and there are more precise simulations which have been done by Jean-Louis Barra in Lyon. If you take a tissue in the homeostatic state, if there is no cell division, no cell death, it's like a glass. It's a disordered system, and it reacts as a solid, and if you put a large stress, it flows. If you add cell division and cell death, so of course if you want to maintain it in a steady state, you have to make them equal, this yield stress vanishes immediately, which means even at extremely low values of cell division and cell death rate, the yield stress vanishes. So in the end, it's indeed a viscoelastic medium. The last question was more or less answered by the previous speaker. Most people who work with vertex models, they work with tissues in 2 dimensions. The only thing I did myself is work in what he called 2.5 dimensions, just because I wanted to see how much you could derive these vertex model equations in 2 dimensions from the one that include the height of the cell. If the cells are flat enough, there's no problem. You find them exactly. If the cells are extremely elongated, it's not exactly the same thing. And then you have to do it for your own 2-dimensional tissues, which is what was presented to you in the next talk. So I will stop here and thank you for your attention.
So I've seen some vertex models, okay, have using an energy definition where P0 is equal to 0 and there's no square. I'm meaning that motivated by this coefficient is the surface tension and it's just minimizing the surface. Then in that case, there would be no disordered. And what's your opinion?
Okay, so that's one drawback of my generalized perimeter. Vertex model, as you wrote it, or as I wrote it in the first slide, you can make sense of all the terms. So you can say there is something that wants to minimize the area and make it to an area A0. And then you say there are all these edges, and these edges are under tension. And you know that this is true. You know what it depends on. I mean, there is a contribution to the cell cortex, which is a contractile where you put your contractility. So you know that these tensions are there. Now, the plot that I say that I didn't want to go into that because I felt I didn't have enough time, but the plot that I showed with the ground state was plotted like this, which means one of them was a tension and the other one was some of the moduli. So the linear terms, which mean the constant term plus the linear term you get out of this. Then there is a term proportional to p squared. This one is harder to decide where it comes from. If you look, so the first, I mean the names are on my slide, but the first person who did it was François Graner from Université de Paris, it's called now. And I'm just provoking people. And he had this linear term that you were talking about. This quadratic term was written, I think, by Frank Jülicher first. And what he says is that line tension, because the surface tension in 2 dimensions is a line tension, depends on the activity of the cells, and so it should have terms proportional to the perimeter. The only thing I can say is that if you take the most naive, what you call 2.5 vertex model, you get this term. So just by doing it stupidly, we assume that the thickness is small compared to the radius of the length of the edges, and you get a term proportional to you get this term almost exactly. So, but then you could criticize the way I do the 3D vertex model. So the first 2 terms and the tensions exist. I mean, there's a cable of actin on top of the cells. People know how to cut it, and that decreases the tension. I mean, that's well established. This one is a bit more dubious.
Are there other questions? Just a very simple question. Can you give us examples of the soft, hard, and marginal tissues in our body?
Oh. But most of your... So I got a question which was even worse than this. I can even quote the guy who asked it to me, that some of you may know, who is Paul Chaikin, who is a famous physicist from NYU. I told him the story about the homeostatic pressure, so my first slide. And he looked at me and he said, but then a giraffe doesn't exist, because if you put the weight, it's going to be, and it's orders of magnitude, it's atmospheres, and the homeostatic pressures is kilopascals. And he said, but then, giraffe should shrink, and everybody has done the experiment, and it doesn't shrink. So you have to be slightly more subtle if you want to do that. I consider the tissue as a one-component system with only cells. This is not true because there is fluid in between the cells. Now, the fluid has a hydrostatic pressure. Now, if you do, from a macroscopic point of view, the theory correctly, you will find that what balances the weight is the hydrostatic pressure of the fluid in between the cells. And what controls the cell division rate is the cell pressure, which is the one I was talking about. So this problem, I mean, if you only look at what I said, it's true. If you do it as a 2-fluid model, it disappears completely. There's another one on a question that was asked this morning on what happens to the cells that die. In this case, I just take them out. If there's fluid, you can say they are part of the external fluid. So the mass is conserved, everything is conserved. And then if you compare, it's not bad to do what I did. There are conditions for that we know, but it's not bad to do that. And it simplifies things highly. Well, this is why I didn't want to go into that, but yes, your question is relevant, but it needs to make a slightly more sophisticated model to solve it.
Okay, other questions or remarks? Okay, so we stop now. Thank you again to the speakers.